Hey guys, I'm looking at a new video in this computer vision tutorial. In this video here, we're going to talk about the stereo vision depth estimation project that we already did in one of the previous videos with C++. But in this video here, we're going to focus on like how we can implement it in Python and how we can do depth estimation where we're tracking an object in an image and then doing depth estimation with stereo vision in Python here. But first of all, I linked Discord server down in the description, so make sure to join that and join the community where you can talk with other people about computer vision, artificial intelligence, deep learning, and a lot of other different kind of stuff. And also, if you have some problems in your project or just want some inspiration for new processing stuff like that, make sure to join that Discord server and join the community. So let's now jump into the first slide here where we're going to talk about the multiview geometry that we're going to use for our stereo vision setup and to calculate the disparity, which we're going to use to calculate and estimate the depth of a point in the image. So we already went over this in the previous tutorials in the C++ project example. So in this video here, we're just going to give you a quick overview over what it is and how it can be used to actually use for this application here. And if you want a more detailed explanation of all of these different kind of parameters and how to find them and what we can use them for. And also, if you want to go over it step by step, make sure to check that video out before we dive into the code, because it's just the same details and the same kind of methods that we're using. But in the previous tutorials, at the end, we went over the C++ code, and in this video here, we're going to do it in Python. So first of all, here we have these two cameras here. So we have this stereo vision setup. So we have a left camera and a right camera, and they're aligned at the same axis. And then we have then the right camera here is placed at a distance away from the left camera here, and this is called the baseline. So the distance between these two cameras here is the baseline, and this is what we're going to use to actually calculate the depth and the disparity of the images, or like the points in the images when we're doing our project. And then we also have this XL and XR here, which is the disparity of a point here in the left image frame and the disparity over here for the point here in the right image frame. So we're going to calculate these disparities, or these disparities from the left optical axis here out to the point in the left image frame, and the same thing over here to the right. So and then we can calculate the overall the disparity for this point that we're tracking in the image. And in this example here, we're actually going to track an object that is moving around in the image. So we're going to track a red item or a red object, and then we're going to calculate the depth to that item that we're tracking in the image. So to calculate the disparity over here, we just subtract this this distance here, or this difference here from the point to the optical center of the left here, and then we subtract it with this XR value here. So we went all of these formulas up here and what these different kind of parameters and values are in the previous video where we went over the project. So make sure to check that video out if you want to know how we can get these different kind of formulas and what this C distance is, and also the F distance and the X distance here and stuff like that. So we already did this code example here in C++ with the depth estimation where we're finding the depth and where we're using these formulas that I just showed you on the previous slide. And then over here to the right, we have this mask image here. So we're going to do a segmentating of a color. So in this case here, we're segmentating out the red color. So first of all, we're going to convert it to HSV color space, and then we can actually filter out the red color that we're going to track in the image. So we have this object here that we're going to track, and then we're going to find the contours, find the center of mass, and then we're going to track that item around in the image with our stereo vision setup. And when we're tracking the same item with our stereo vision setup, we can actually calculate from the center of the object that we're tracking in the image. Then we can actually calculate the disparity for that, and then with this disparity we can calculate the depth, or the distance to that object that we're tracking around in the frame. As we see here, this is the result that we get from the code example in C++. So in this video here, we're going to do it in Python, and it will be the exact same methods and the exact same formulas and approach that we're going to take. So this will just be in Python instead of C++ if you prefer Python over C++, or if you just want to use or if you have a Python application where you just want to implement this here and you want to do it from yourself from C++, then I'm going to give it to you here in Python as well. So first I just wanted to show you this drawing here that I did for the multiview geometry here. So this is the actual approach or method that we're going to use for actually getting the information about the depth in the image from our stereo vision setup. So as we have here, we have this red point here that we can remove around here in the world coordinates, and then we can see that it will make a projection down here on the left image frame and also the right image frame here in the cameras. So we can see that if we're moving this circle here around, or like this object here around in the world coordinates, then we can see that our point on the image frames or like image plane is actually like moving. And we can see that if our object is close here to the image frame or like to our camera lens, then we can see that the change in disparity is greater. So we can know that, and we can use that information to actually like calculate the depth and know like how far away is that object from the camera. So if we move further away here, we can see like the changes here in the disparity is not that great. Like we don't have like a great value when we're changing the point here when we're moving further away. And if we align the point here with one of the left optical axis, for example, we can see that if we move closer here, that we can see like we don't really get like we get really large disparities here, and then when we're moving closer, like it just gets smaller and smaller, the disparity. And if we get like too close to the left image frame here or like the camera lens, we won't be able to see it in the right camera. So we can use this information here from the second camera. So if you only have one camera, we don't have any information about the depth here. For example, in the left camera frame here, we don't have any information about the depth, but we can see that the point here is actually like moving in the right camera here when we're going up and down here on the left optical axis. And this is the information that we can use to actually like calculate the depth from these disparities here in the image frames. So we're now into the Sublime Text here, and I'm going to show you the actual code that we're going to do for this project here. And then at the end of the video, we're going to run the project and see how it works with this stereo camera setup. So first of all, here we're going to import the different kind of modules that we need. So we need like, for example, NumPy, OpenCV2, some time, uMutils, Matplotlib, and some other stuff like that. And then we're going to create our own functions in these different kind of files here, where we have the HSV filter that we're going to do, and then we're going to do some shape recognition of the object that we're going to track, and then we're going to do the triangulation here in this file, where we're actually like going to calculate the depth from the disparity in the images. So first of all, here we're going to open up both the cameras here. So we have a capture for the right camera and also a capture for the left camera. And then we're going to set the different kind of parameters here that we have for our cameras. So first of all, here we're going to set the frame rate to the maximum frame rate at 120 FPS, and we have a baseline, which is the distance between the two cameras that we have in a stereo vision setup. In this case here, they're 9 centimeters away from each other, and the focal length from the camera, which is the distance from the camera lens to the image plane, is 6 millimeters. And then we also have like a field of view here, which is our alpha value. Then we're going to run our while loop here. So this is just like this program here will just keep running until we terminate it or hit the Q bottom at the end here. So first of all, here we're going to first read in the return frame right here or return left, and see like if we cannot open the frames, these will return false. And then we store it in this frame right here and frame left here. So we have to, like, what we're capturing with our left and right cameras will be stored in these frames here, which is the right one and the left one. And then we're going to have the camera calibration here. So ideally we'll first have to do camera calibration, but we won't go over it in this video here. I created another video previous in this tutorial here where we went over camera calibration and how we can calibrate a camera and why we should calibrate a camera in OpenCV and just in computer vision programs or applications in general. Because if we have a really distorted image and we're going to do and calculate these disparities here, there will be distortion and our estimation of that will not be exact. So we need to calibrate our camera first before we're doing this if we have a lot of distortion on our images, but we want to doing it in this video here. So make sure to check that video out if you're interested in camera calibration and how we can calibrate a camera for your application or your project that you're doing. So first of all, here we're going to see like if we cannot catch any frames from either of the two images or like the two cameras that we're going to capture. Then we just break out this while loop here and it will just terminate the program. Or else we will run the different kind of methods here that we're going to go over in the different kind of files here. So first of all, here we have this mask right here and the mask left. So we want to get the mask of the item or like the color that we're segmentating out. So first of all, we're going to call this HSV here, which is from the file up here that I'm going to show you. And then we're going to add this HSV filter here to the right frame here on the right camera. So if you go into the HSV filter file here, we can see that we have this function here, add HSV filter, and it takes in a parameter, it takes in the frame. and it takes in what type of camera, so if it's the right or the left camera. So we're going to use this because I don't have two identical cameras for this application here, where we're going to set this stereo vision setup up. So I have some different kind of colors for the HSV color space, so I have to filter out two different colors. But if you have the exact same cameras, you can just only pass this frame here, and you can just use the exact same values for the lower limit and the upper limit for segmenting out a color in the image. So first of all, here we're going to blur the flame to blur the frame here to reduce some of the noise from our camera. So first of all, here you're just going to call this cv2.gaussian noise, and then we have this frame here where we apply this 5x5 filter kernel here that we're going to blur out the frame with. And then after we've blurred out the frame, we're going to convert it from RGB to HSV. So we have this HSV color frame, color space here that we can actually like. So only have the hue, saturation, and value. So we can actually like just filter out a H value, so it's a hue value. So we can just filter out an exact range between those hue values. And then we're going to create a lower limit for the right image, and a lower and upper for the left image as well. So first of all, here these are just the HSV values that we're going to filter out. So in this case here, this is for filtering out the red ball, or like segmenting the red ball in the image, or like the red item or object that we're going to track. So if you have some other different kind of colors you want to track in the image, then you need to go in and change these values here, like to the hue value that you want to segmentate out in the image frame. So after we've done that, we go down here and we're actually like going to apply this filter mask here, where we're going to segmentate out from the image and like the object that we're tracking, and we will then create this mask here, which will be returned that we can do some other operations on. So first of all, here we check if it's the right camera that we're operating with now. Then we're going to do to have this in range function here, where we filter out or like segmentate out these colors here that were specified in the lower and upper boundary up here for our right camera, and then we're going to store it in this mask here. And we do the same thing if it's in the left camera, if it's the left camera that we're using, but then we're just using the other different kind of lower limits and upper limits that we have set up up here. So when we've done that, we're actually like created our mask here for our camera frames, and we have segmented out the color that we want to track in our image. And then after that, to do some other different kind of image processing and reduce more of the noise in an image, then we can actually like use the morphology operations, which we've already been over in one of the previous videos in this computer vision tutorial here. So the mask here is equal to this cv2.erode, where we're going to erode the image first. So we have these parameters here, which is just default parameters that we pass to this erode function here. And then after we have eroded the mask here, we're going to dilate it. So when we're doing this combination of erosion and dilation, then we actually call it opening. So we're doing the morphology operation opening on our image to reduce some of the noise and like open up some of the different kind of like noise inside of the segmentating that we're doing of the object in our image frame. And then when we have done that, we're returning this mask here, which is the mask that I showed you in the slides as well, where we have this white object that we're tracking around, which is the actual mask that we have for our image. So if we go back here to our main function, then we can see that we actually like apply this HSV filter here, both for the mask of the right image and a mask for the left image here. And then when we have this mask here, we can actually like calculate or like take the resulting frames after applying the HSV filter mask here. So we have this resulting right frame here and the resulting left frame here. So when we're going to do this here, we're going to bitwise AND the right image frame and the right image frame here, and then we're going to AND it with this mask here that we just got from this applying this HSV filter up here. So we're actually like segmentating out the object in our original frame by using this mask over here to the right that we calculated with this HSV filter. So then the resulting frame here would actually like store the resulting frame with the object that we're tracking, and we do this both for the right image and the left image here. So when we have done this here, we can actually like apply some shape recognition, where we're going to find the circles or like find the object that we're tracking in the image by using this find circles function here. So if we're going to the shape recognition file here, we can actually like see we have this find circle function here, and we pass in the frame and also the mask that we're going to use to find these circles here, or like find the biggest circle or like the biggest object that we're going to track in the image. So first of all, here we're going to find contours in the image that we're going to track. So we just use this function here with the default parameters in OpenCV. And we're going to use these functions here, which is just like how it finds contours in the image, and then it will be stored in this variable here. So all the contours that it finds will be stored in this variable here, and then contours here we're using this IMUtils where we're grabbing the contours in contours here. So we will grab we will first sort the contours here with this function, and then we're going to grab the biggest contours in the image. And then first of all here we set the sender here to none, and then we're down here we're actually like going to proceed if at least one contour was found, and if one contour was not found we'll just like return the sender here which is none, so we know that we haven't found any objects or circles in our image. But if we find some contours in our image, we're going down here and then we find the largest contour in the mask, and then we use it to compute the minimum enclosing circle and the centroid of that circle, so we actually like know the middle point that we're going to calculate the disparity for of the object that we're tracking in the image. So first of all here we're going to take this C here, which is the max of the contours, and then we use this CV2 contour area. So we're going to take the contour with the greatest area in like inside of the contour, and this will be stored in this C variable here. So this will be the biggest contour that we have. And then we have this X and Y here and the radius. So this is the actual like circle that we're going to draw around our object, and we use this by using we get that by using this min enclosing circle here, which will turn the X, Y, which is the center of the circle that we're tracking, and then we'll also get the radius of the circle here around our object that we're tracking. So to find the actual like center point here for our image or like for the object that we're tracking, then we use this moments function here where we can get this C value here, which is the maximum contour that we found, and we will store it in this M value here. And then to actually like get the center values for this moment here, we have to use some of these functions here, which can be found in like some of these different kind of parameters for the moments, which can be found in the OpenCV documentation. And then it will be stored in this center variable here. So now we actually like have the center of the contour that we're tracking, and we also have the X and Y value. So then we can go down here and only proceed if the radius is greater than a minimum value, because we can find some different kind of contours that is not as big as we want to, or like some false positive that we don't want to track in our image. So we can go down here and see that if the radius is greater than 10, then we will draw a circle and the centroid on the frame, and so we can actually like show the result of the circle that we're tracking in the image, and then we can update the list of the track points. So to actually like draw the circle and the centroid on the frame, we just use this circles function here from OpenCV, and then we're going to draw the circle on the frame here, and we're going to draw it at the center of the circle that we have calculated up here. And then we also use the radius here, so we're going to have this radius here. So we're actually like going to draw a circle around the object that we're tracking, and we also draw like the center of that circle here with this center variable here that we calculated up here from the moments. And then when we're done with that, we just return this center value here, and it can either be none or it can be this value up here. So we can actually like use this center here to actually like do some other different kind of operations when we're going to calculate the disparity of the two, of the point in the two images. So if we go back here to the main function, we can see that we will store the circles here in this circles right and the circles left variable here, and we do that by just calling this find circles here, where we pass the frame we want to find the circles in, and also the mask that we just calculated up here by applying this HSV filter. So now the circles that we're tracking in the two images will be stored in this circles right and circles left here, and then we can use these two different kind of like these variables here to actually like do the triangulation and calculate the disparity and the depth of that item or like object that we're tracking in the image. So instead of finding contours and stuff like that, we can also use some Hoff transform, which we also went over in this tutorial here as well, to do the object detection, which will also return like the center of the object that we're tracking, or we can use some neural networks to do object detection. So a lot of other different kind of object detection algorithms and stuff like that can be used together with this here. And then to find the third dimension and the depth in the image of that object that we're tracking, then we can actually like use this this stereo vision setup and approach here that we're going to take to actually like calculate the disparity and the depth of the image, and then we have this 3D understanding or 3D information of the objects that we're tracking in the image. So to actually like calculate the ball depth here, we go down here and see like if no ball can be caught in one camera, we just show the text on the image that we're outputting or like showing that the tracking is lost. And we do this by just using this put text here. We're just going to put this text here, track lost, and then we have some colors and where we want to place that text on the image. Or else, if we can actually like catch an item, or like we're tracking an object in our image frame, then we'll go down here and we're going to calculate the actual like depth by using this find depth from the triangulation file. And to find the depth here, we're going to pass the circles in the right image frame and the circle in the left image frame, and then we're going to pass the two image frames as well. And we also need the information about the baseline, so the distance between the two cameras in the stereo vision setup, and the focal length, and also the alpha value here, which is the field of view. So let's go into the triangulation file here and see like how we can actually like find the depth by using these formulas that I showed you in the slides. So first of all, here we need to convert the focal length from millimeters to pixels to actually like be able to do these calculations with pixel values from the images. So first of all, here we're going to get the height from the right image frame, and the width, and also the depth, and we get this by using this frame, like we're calling this shape function here on the right image frame, and we do the same here for the left. And then we can check that if the width of the right image frame and the width of the left image frame is equal to each other, then we're actually like going to calculate the focal length in pixels, because when we're doing stereo vision, we need the width of both cameras to be the same, or else we can really use this approach to calculate the disparity and find the depth estimate information from that if we don't have the same width of the two cameras, or like the pixel width for the two cameras. So to actually calculate the focal length here in pixels, we just use this formula here, which is just a standard formula for converting from millimeters to pixels with this focal length here. And if those two width here is not the same, then we just print out that the left and right camera frames do not have the same pixel we use. Or else we go down here and find the disparity for the right circle and the left circle, and then we'll store it in this x right here and x left here, which is the values that we also stored in the slides. And then to calculate the disparity here, we just subtract these two values here from each other. So the values in the x and the left, which is the distance from the point in the image frame to the optical center in the image. So when we have our disparity here, we actually like have the displacement between the left and the right frames, and then we use this disparity here to actually like calculate the depth of the item that we're tracking in the image. So to calculate here, we have this C depth value here, which is the actual like depth of that point that we're now calculating, and then we need this baseline information here, which we pass in as a parameter up here in the function, and then we multiply that by the focal length in pixels, and when we have that value, we'll actually like divide it by the disparity that we just calculated up here. And when we're done this here, we can actually like return the absolute value of the depth value here, and then we actually like have information about how far away is the object that we're tracking in the image, and like how far away is it from the camera. So then we're going to return this value here, and then we have actually like found the depth of the circles that we're tracking in the image. So if we go back here to the main file again, we can see that we will now store the information about the depth in this variable here, and then we can just output some text on the image frame again that we're now tracking the object, and we also output and display the distance to that object here on the image frame, both the right image frame and the left image frame, and then we'll print out to the terminal the depth of the image as well, which is the same as that we're going to show on the actual like frames. Then down here we can show the actual frames, so we're going to show the left frame and the right frame here, and then we're also going to show the mask that we're getting from applying this HSV filter here, so we can see like what information do we get and what information are we actually like tracking. And then down here we have this hit Q to close the window, and when we hit Q in this while up here, it will just terminate our program. We will release the capture for the right and the left image, and then we will also destroy all the windows, so we can actually like open up the camera later on again and close them when we're done using. So this is the actual code here for doing this stereo vision and depth estimation using stereo vision in Python. So now I just set up the stereo vision setup here, so we can actually like see how we can use this when we run the program. So let's run the program here and see how this application and project here works. So I'm now running the project here by hitting Control B in Sublime Text here, and we can see that now I'm coming up on the image frame here. and we can see that we've lost the tracking here in the image, and we can see that we're not segmenting anything out here on the right and also the left image frames here. We can see that I don't have two identical cameras here, so the color is not exactly the same, and that was why we needed the two different kind of upper and lower ranges in our HSV filter. But we can see that the image frames, like the width of the image frames here, is the same one, so we can still use this for our stereo vision setup. So if we check this object up here, we can see that I have this kind of like shoe here that we're now tracking in the image, and we can see that the mask down here is returning like it's pretty good. It's pretty good segmenting out this red color here from the image, and we can also see that our morphology operations with the opening that we did is reducing a lot of the noise inside of the actual like object here that we're tracking. And we can also see like now we can see that it is tracking up here, so we can see that it is now tracking the object up here at the top here, and it says tracking, and then it also displays the distance that it's calculating from the disparity to this object here that we're tracking. So if we move this object here closer to the stereo vision setup here, we can see that the distance up here gets less and less the closer we come to the camera. And then we can also see like if we move further away, like right now I'm around 1 meter away from the camera, and this is actually like a really exact calculations of the depth here, or like the distance to this object here, because I'm actually like right now 1 meter away from the camera. So if we move closer again, we can see that now we're at half a meter towards the camera. So it's a pretty good estimation of the depth in the image here by just using this symbol application, or like this symbol code here that we did in Python. So it tracks it pretty good around. We can see that it keeps track of the circle. We're segmenting out the color really good here on the mask, and we're actually like calculating the distance, really nice approximation or depth estimation. So this is a really cool, nice project that you can do in your own application, and you can use this code here as well if you have some stereo vision projects that you're doing. So thank you guys for watching this video, and remember to hit the subscribe button and bell notification on the video, and also like this video here if you like the content and you want more in the future, because it just really helps me and the YouTube channel out in a massive way, and it really motivates me to do a lot of other different kind of cool projects like this here that can be used in a lot of different kind of modern computer vision and OpenCV applications and projects. So I'm currently also doing a deep learning and neural networks tutorial. So if you're interested in that tutorial, I'll link to it up here, and we're actually like going to combine it with OpenCV and computer vision later on. So thank you guys for watching, and see you in the next one. Bye for now.